Hello geometry students, this is section 7-4. I messed up the title on some of the notes that I printed, so if your title does not say similarity in right triangles, can you change your title so that it does say similarity in right triangles? The learning target for today is students will apply the geometric mean to missing sides of right triangles. And here's a definition. The geometric mean between two positive numbers a and b is the number x such that x equals the square root of a dot b. Now yesterday, you'll remember that we were working with right triangles and we would draw the altitude from the right angle to the hypotenuse at a 90-degree angle. And when we did that, it created two similar triangles to the original larger triangle. So we really have three similar triangles that we're looking at. We have this red one, we have this yellow one, and then we have the outside one, the larger outside one. So we're really looking at three similar triangles. So let's look at how the geometric mean is derived. We showed earlier that these are similar triangles, we said yesterday, and therefore they have this following ratio. AD is similar to CD, and so we write that in the top of our proportion. Then we have DB is similar to AD, and that is written in the proportion here. And you can see, like, we're comparing the shorter legs, and then on the denominator we're comparing the longer legs. You could also compare the hypotenuses. Is that a word, hypoteni or hypotenuses? I don't know. Octopi, octopuses. So we can prove the geometric mean because when we cross multiply these, we would get AD squared equals CD dot DB, and that would mean that AD would equal the square root of CD dot DB. Now we're going to apply that to this next problem. All right. We have we're trying to figure out what CD is in these similar triangles. And we can write a proportion. So we're looking for DC. And DC is part of the smallest triangle and it's part of the medium triangle. So in the smaller triangle, DC is the longest leg. I'm just going to color these triangles just to make it a little easier to see. We have this green triangle that we're looking at, and then we'll have this blue triangle that we're looking at. All right, so DC is the longest side of the blue triangle, but 6.4 is the longest side of this triangle. So we compare those and we would say that DC is equal to AD, right? Because those are the corresponding sides, the longest leg. And we know, and we can just kind of keep this over here in a thought bubble, that AD is equal to 6.4, which is helpful. Now, with the geometric mean, we're looking for DC, and so we're going to put DC across from each other. But now this is talking about the big green triangle, this side of the proportion. And DC of the big triangle is the small leg. So the small leg of the big triangle is DC. And the small side of the blue triangle is DB. So we would put DB right here because DB, the small side, corresponds to the small, or the small leg corresponds to the small leg of the big triangle, which is DC. And we will say that that is equal to 3.6. And the small triangle was blue. Now we just need to do the geometric mean, which says we're going to cross multiply, so 3.6 dot 6.4 is equal to DC squared. Those are the cross multiples. Then DC would equal the square root of 3.6 dot 6.4. 3.6 times 6.4 is 23.04. And then in my calculator, I'll take the square root. The square root is 4.8. And that is what DC equals. So you could draw an arrow showing that that is the length of DC, 4.8. And it makes sense. If we look at the diagram, if it's drawn to scale, it looks like that would be 4.8. On this next page, we have a triad problem. And we're asked what CD is. Now, the geometric mean says that we can take these two pieces that are cut by the altitude. If we multiply them together and take the square root, that'll give us the length of the altitude. So I will take 5 times 15 and take the square root. 5 times 15 is 75. There is no perfect square root of 75. So I'm going to teach you how to break that square root up into its prime factors, which would be, well, we know it's 5 times 15, because we just got that, and the factors of 15 are 3 and 5. So the prime factorization is 5, 3, 5. 5 times 3, 15 times 5, 75. There are two 5s, so 5 times 5 is 25, and the square root of 25 is 5. So we can take a 5 outside of the square root, or outside of the radical, and leave the 3 inside. So if it asks for an exact answer, that's what you want to do. For part B, it says describe how you can use the value you found for CD to find AC and CB. All right, well, CD is this. And the way that we will do this is we will set up a proportion. Excuse me. And we're trying to find AC first. So to find AC, AC is on, I'm just going to draw it again. AC is here, which is part of the small triangle, and it's part of the larger outside triangle. All right, so we are dealing with this inside triangle, and we're also going to deal with the outside triangle, the whole thing. All right, since we are looking for AC, we're going to do AC of the little triangle, the blue one. That would be the hypotenuse of this little triangle, A to C. And so the hypotenuse of the larger triangle is AB. And we know that AB is 20. because 5 plus 15 is 20. Second thought myself, that's 20. And I'm looking for AC, and so what we do at the geometric mean is we put the AC across from each other diagonally. Now I'm looking at the big triangle, the pink one. So AC in the pink triangle is the little piece. It's the little leg right here. Well, the little leg in the smaller triangle is right here, which is from A to D. And A to D, we already know from the diagram above, was 5. Because I just drew this triangle from this one. These are the same triangle. I just redrew it so that I could highlight it up. Well, now we would just do 5 times 20, which is 100, and take the square root. I guess I should show that step. 5 times 20, that is going to equal the square root of 100, which is equal to 10. So AC is equal to 10. And I should just be consistent that this was the small triangle here that we did. Sorry. So this is your answer, AC equals 10. Now, the other part of it asked what CB is. And so we can do a thing. We'll set up a proportion. CB is what we're looking for. So we'll put them across from each other like so. CB is on our medium triangle, which I will color in for you. Our medium triangle right here, the green one. So CB is part of the green triangle, and it's also part of the outside pink triangle, but it is not part of the little triangle. So we're not going to deal with the little triangle. CB on the green is the hypotenuse right here, the hypotenuse, which corresponds to the hypotenuse of the big triangle. And the big triangle, the hypotenuse is AB, which is equal to 20. Then we're looking at the green triangle, or actually, I'm sorry, we want to know what CB is on the pink triangle. Well, on the pink triangle, it's right here, CB, from here to here. And on the pink triangle, that's the long leg. We have, I just want to double check in my diagram. Yeah, it's CB is the longer leg. And the longer leg of the green triangle, the longer leg of the green triangle is right here, DB, which is equal to 15 from the diagram above. And then we just cross multiply, so 15 times 20 would be 300. So 15 times 20 is equal to 300. And if I wanted to find the factors that come out, I could say it's equal to 3 times 100. And 100 is 10 times 10. I wrote that horribly, but 10 times 10 is 100, or the square root of 100 is 10. So a 10 can come out of the radical, leaving the 3 inside the radical. And that is what our CB would equal. Let's try some more problems. We have the triangle JKL, and it's asking what is JL? So what is this? So we'll just set up a proportion. We'll take JL is on the small triangle, and it's the hypotenuse. So we'll set up a proportion like so. JL in the numerator across from JL in the denominator. Of the small triangle, it's the hypotenuse. I'm really sorry about my dog. But in the large triangle, JL, the hypotenuse for the large triangle is this piece, JK, which is equal to 24. All right, now we're looking at JL. In the large triangle, it's the small piece. But in the small triangle, the small piece is JM, and JM is equal to 4. So all we have to do is multiply 24 times 4, take the square root. I'm not even going to multiply it because I know that 24 is 6 times 4, which gives us 2 4s in the radical. 4 comes out, leaving 6 inside. And that is our answer for what JL equals. What is KL? I'm just going to clear all of my highlighting from before. KL is right here. KL is associated with the big outside triangle. So we'll write KL in our proportion. And in the large, or let's first talk about it. It appears in the large triangle and it also appears in the medium triangle. So it also appears in here. Okay. In the green triangle, it's the hypotenuse. Well, the hypotenuse of the outside larger triangle is JK. JK is equal to 24. Then we're looking at KL as it relates to the big outside triangle. And KL in the big outside triangle is just the longest leg. And so the longest leg in the green triangle is from M to K. And M to K is 20. So we're going to do 24.20, take the square root, and 24 is 6 times 4, and 20 is 4 times 5, which means we can take a 4 out, leaving 6.5 inside. Those don't really have any factors in common. Like I could factor 6 to be 2 and 3, but I would just have 2, 3, and 5, no pairs. So this just equals 4 square roots of 30, and that is what KL is equal to. In example 5, we are using the geometric mean to solve problems, and that means that they're asking us to do some algebra. We want to know, what is the value of x? Well, we have this x, and we have the altitude. Well, if you remember, we can take this piece, x plus 5, and x, multiply those together, and it'll equal this 6 squared. Or we could just set up a proportion. So we have x plus 5, and that is the long side of the medium triangle. And we have 6 is the long side of the small triangle. Then we have x here, and I apologize, my dog is playing in the background. And x corresponds to the 6. We cross multiply, and we get x parentheses x plus 5, and we get 6 times 6 is 36. There is a way to solve this using quadratics, but I'm just going to kind of take you through some guess and check. So some people were saying that 6 times 6 is 36, which is true, but if I put a 1 in for the x, that would give us 6, but that would be 1 times 6. So that doesn't work. And then somebody told me that 9 times 4 is 36, and so if I plug in 4, that does equal 36. So x is equal to 4. Example 6 is apply geometric mean to find distance. Zhang is constructing a 4-foot high loading ramp. The length of the back of the base must be 12.8 feet. So in the picture, that's talking about this piece right here. And they're asking, how long must the entire base be? But before I can figure that out, I need to figure out what the front part would be. So I'm going to compare the two triangles. If the back is 12.8 feet, that corresponds to the long leg of the small triangle, which is 4. And then the short part is the front. So the front wait, I think I did this incorrectly. The back is 12.8. And then, okay, and then we would have 4 is the short part of the medium triangle, and the front part, I'll use F, is the short part of the small triangle. So let me just highlight what I mean by that. So like if this is the small triangle, then that would be these numbers. And then if this is our bigger triangle, that would be where these numbers came from. So we're just gonna cross multiply and divide. So 4 times 4 is 16. And then we can divide by 12.8. And that'll tell us the front piece. So 16 divided by 12.8 is 1.25. So that's the front piece. If this is the front piece, 1.25, then to answer the question, how long must the entire base be, we have to add the 1.25 to the back. So the back plus the front equals the base. The back was 12.8, the front was 1.25. So the base will equal, let me see if I can do this in my head, 1314.05 feet is how long the entire base needs to be from the back of the truck. All right, and that concludes your notes for 7-.